Good afternoon. Um, this lecture has been prepared by our group, and this is our group. I am Rupam, and I would take you through the topology and control of switching regulators. Just before this lecture, you heard a very interesting talk by Professor AP, in which you are given a broad overview of what these power management circuits are all about. So what I would do, I would take a small subset of these circuits and take you through the basic, not in depth, but basic design steps and the control strategies involved. So let's get through it. You have already seen this, why the voltage regulation is necessary, because there is change in load current, huge load current change, as has been mentioned, about 120 amperes per microsecond. This sometimes happens in processors, as you have already noticed. And then there is change in supply voltage also, because battery will get discharged slowly and slowly, and we need that the output voltage should be maintained constant. Hence, output voltage must remain constant. This is very important. Hence what are the basic requirements? Just what I would be doing is that I would first take the requirements, and then I would try to get you through the kinds of waveforms and behaviors that are necessary, and follow a kind of top-down approach, and just go through this buck converter topology, which you have already seen in a bit different way, so that you get more used to it and you are able to design it efficiently. So we need a circuit that gives a variable output voltage and a method of controlling this output with a suitable feedback, because we need to know how the output voltage is varying and accordingly take control action. Hence, we have a power conversion stage and a controller. We need to design these two separately, and before we get to design, we will need the block level specifications and the behavior, whatever is necessary for these two blocks. So this is the power conversion scheme that you have already seen. It's a switching signal. It's being passed through a low pass filter, which incidentally you have already seen is a LC network, and this will give a variable DC voltage. This DC voltage is the average. Here, as you can easily see, for D1 TS and D2 TS, this kind of circuit, the average will be D1 of V in and D2 of V in, right? However, something was mentioned regarding volt second balance, as you have already heard. Now, why do we need to at all consider volt second balance? Here we can straight away, through your averaging, we can say that our output is this much. But there may be certain other topologies in which this kind of taking a switching signal and putting an averaging, this kind of simplistic technique might not be very easily applicable. I'll show slowly. And hence you should also learn about the volt second balance, and this is the rudimentary crude way of getting the output voltage, this averaging thing. And when you apply volt second balance, that will be the engineer's way of getting the output. That will help you solve a wide class of circuits. Well, before we go to control logic, I will just show you how to derive this, what this dV in kind of expression comes from. Let's say if this is my power circuit, these are the two switches, as has already been shown, two switches operating in complementary mode. When this one is on, so I'll mention one by this, I'll indicate. So this will mean that these two are complementary in nature, and then we have this, and then load. Right. So the nature of inductor is volt second balance. What does this mean? Say this switching signal, I mark this as D, on period of this as D. So it is important to identify your reference of D whenever we do any such analysis. So if this is D, say this is DTS, then this is 1 minus D TS. When this is on, during DTS, the circuit configuration will be like this. Right. So at first we assume that the output voltage is constant, and slowly we will explore ways of how to make it constant. That's when we design the controller. So when output voltage is constant and this is V in, what is the difference? The volt difference across this. Volt difference is V in minus V out. And for how much time this persists? This thing persists for dTs, right? So this will be dTs, volt second, volt into second. Next, when it is 1 minus dTs in the complementary switching mode, your circuit configuration will be something like this. Then what happens? Then it is 1 minus dTs into V in minus V out earlier. So this one is minus V out because this side is 0 obviously. Now when we say volt second balance, it means the total of the volt and second, it will remain constant. This difference will be 0. All right. So this plus this is equal to 0. Where does this comes from? This comes from if this circuit has to be stable, it cannot blow up. Suppose your inductor current blows up like this, it is unstable. But when we are designing the circuit, we are designing it for stable operation. For stable operation, this has to be bounded. Okay, this has to be, say, for initially you may consider that for stable operation, this has to be periodic, right, every cycle. So the magnetic energy, that is total stored in that, or in a more rudimentary form, the flux in the core of the inductor, that has to be conserved, that will remain constant. So this thing will be 0. Once you work this out, this will come to, this expression will lead to your V out by V in equal to D, this expression, right. This is in fact whatever we get from the averaging concept, where we consider this as a low pass filter and average the square wave, we get the same thing. Now I mentioned that there may be certain topologies in which you won't be able to simply average the stuff and get the expression, and that's the reason why we are studying this volt second balance. So let's look at the boost converter. That's another very basic converter in which it will be a bit difficult if you are to apply a crude rudimentary averaging kind of method. In that case, you really need this volt second balance, otherwise you can't derive the expression. Say when you are considering the boost converter, so this is a boost converter, this is the boost converter, as you have seen, this will have this and load, right. Now when you consider the two circuit nodes, two configurations in which once it is connected to this and another time this is connected to this, you cannot just isolate a square waveform. Here in the earlier form you could say that here it is a square waveform because one side is constant, this is V in, here it is in between two circuits, alright. It will be a bit difficult. And also even if I consider that, let's say we assume that V output is constant and we say this is V output, you will get a square wave here, but then you don't have a capacitor here, so it's not very straightforward. You'll have to do a lot of Thevenins and all that stuff to average this out. So let's apply the volt second balance and practice it. Say I again mark, remember that while doing volt second balance, do not interchange the inductor topology, I mean your orientation, plus minus this thing should remain same. So let's say when I connect to this, I mark it as D. For dTs time period, the circuit configuration will be this thing. Then what happens? dTs into V in minus V out, this thing. Next what happens? We are considering the inductor only. Next the inductor is directly shorted to ground during the 1 minus dTs time. In this case it is just V in. Solve this algebraically, you will get V output by V in equal to well, let's see how much this should be. You should try to solve this, dV in minus dV out plus this thing is equal to 0. So what comes here? V in minus dV in, this is equal to 0, right. So you will cut this out. So what happens? D V out equal to V in. So this is an inverse expression. Hence, V out by V in is 1 by D, which is greater than 1. Hence, this is a boost. Right. So magnification, as you saw that curve, M curve in the previous lecture, it's this thing. Since it is parabolic in nature, 1 by D, or well, or hyperbolic, whatever it is. I just correct me if I am wrong. So it will be a nonlinear in nature. So in this way, you get how the boost converter works. And thus, if you master this concept of this volt-second balance, if I give you any arbitrary converter topology having any crisscross connection of inductors, capacitors, anything, you can get the output voltage expression. So that's why you need this. Now let's put this aside. We now know the volt-second balance. We know how to derive the converter output voltage. Now let's look at how to get the controller, what the controller is all about. I assume that you have not gone through the formal control systems course, which so far as I estimate it is taught in 3rd year. So just I will take it up from a very basic level. Let's say V out equal to dV. Now we return back to the buck converter and base rest of our lecture on this only. So V out equal to dV in. This tells us that increasing the duty cycle will increase the output voltage. Now just look at the cause effect thing. When I say increasing duty cycle increases V out, that means I am considering duty cycle as the cause and the V out as the effect. You must take care of the causality. So when I am considering the plant in control system terms, there is something called plant. If you open any control system book, you will find this kind of a this kind of a diagram where you will find something called CS, which we call the compensator. Just I keep in mind this diagram. You may just note it down so that you can have it for reference, because I will be frequently referring to compensators and plants while I will discuss my slides. So you won't be having this on the screen always, maybe. And then there will be something called plant. This is a general control system diagram that you will find in any control textbook. Okay, this will be the output, and then this will be feedback, right? So here there are several things. Suppose the plant is the system that I want to control. Here what do I want to control? My system is the buck converter. That's what I want to control. So I refer to buck converter as the plant. It may be anything, right? You will go through the op-amp course in your analog. It's not over right now. Op-amp has not come yet, right? So you will go through the op-amp. There also you will find that it's a control system. There you will have to stabilize the op-amp. You will have to make way for good phase margin, and all these things will be told there. There will be feedback. There will be Miller capacitance. So I will try to give you a basic introduction of all these, so that it not only helps you in your power management course, it also helps you in your analog course later on. So there will be a plant and there will be the compensator. Now just imagine, suppose I write here D. Suppose this is the duty cycle. Okay, just suppose, and this is the V out. Now what we have? A system in which a certain D causes a certain V out. So this is behaviorally, this is similar to our buck converter. A certain D causes a certain V out. That means when we take care of the causality, D is the cause and V out is the effect, right? Now what does the controller do? When V out increases, that means we want to keep V out at a fixed level. So when V out increases, what we should do? The control circuit should reduce the duty cycle, because reducing duty cycle will reduce V out. So now just don't get confused with the hen and egg problem. It's not like that. Just consider the causality. When we consider the controller, the compensator, just here in case of the compensator, D becomes the effect. In case of compensator, D becomes the effect, and say something called VC. VC is the cause, right? And in case of plant, D becomes the cause and V output becomes the effect. Now in order to close the loop, what we need to do? We need to have V output as the cause and VC as the effect. This will help us control the entire stuff. Hence, when V out increases, the control circuit should reduce the duty cycle. That's the basic requirement of the control circuit. Once we have that in mind, we can go forward and try to get the control circuit. Don't think of any circuit right now, think of the behavior. because if you get the concepts right, circuits can, you know very well how to solve circuits. So I won't be stressing on circuits at all. This is important. Now we come to something called PWM, pulse width modulation. Why? Because PWM is the common technique used in generating the switching signal, the duty cycle signals that I have shown. There will be a ramp, there will be a this we call a sawtooth signal, and there will be something called a control voltage, VC, that I have marked in your compensator plant diagram. So suppose in this PWM, this VC leads to a switching signal. Now you see, in this circuit, when I reduce VC, V control, this duty cycle reduces, and when I increase V control, duty cycle increases. So we have some control on the duty cycle. That part is solved. We can vary duty cycle. Now we need somewhere to vary VC from our feedback of the output voltage that will close the control loop. When V out increases, hence what do our logic say? Our logic says that when V out increases, reduce the V control or VC, whatever you say. So when V out increases, we must reduce VC. This leads to, let us assume this expression, VC is equal to minus K into V out minus V ref, where V reference is the desired voltage. Say 1.2 volt I want to achieve from a 3 volt, 5 volt, n volt supply, whatever it is. So V ref is 1.2 volt and V out is whatever is actually coming. So if I have this action, then VC will be reduced when V out increases. So this gives us a conceptual controller. We now have our controller in our concept. So what remains to be done is to actually get the topology, how to get this. So this is the behavioral system diagram. We have not yet arrived at any topology. We are just looking at the behaviors. So there will be a feedback from the output. There will be Vref. This is something which we call error amplifier, because in effect it is amplifying the error. V out minus Vref, that we call error. That's also a common term that you will come across in control systems terminology. They will call it error. And then there will be PWM, pulse width modulation, in which this VC will be compared with this sawtooth, as we already saw earlier, to generate this PWM waveform. Once we have this kind of topology, we can have the desired variation as is necessary. We have this power conversion stage which will actually give us a variable V output by averaging out, or your volt second balance, whatever you say, by averaging out this switching signal, and this entire control circuit which will actually take this feedback action and vary this switching signal duty cycle. So behaviorally our controller is complete. Now what we need to do is how to get this, what are the circuits actually involved behind these controllers. Okay, let's see. Now we are looking into the sub circuits. This is the converter, as you have already mentioned, that you may consider it as a low pass filter after a switching signal, which concept is inadequate in many cases, like the boost converter that I have shown, and hence you should do it by volt second balance. And then this switch realization, as has already been mentioned by Professor AP, and these are the complementary switching of MOSFETs is achieved. How do we do the complementary switching? We put this as PMOS, this as NMOS, and the same switching signal will actually do complementary switching, because PMOS and NMOS will have complementary, if this turns on at 1, the other one will turn on at 0. PWM, you can easily guess that the PWM is actually a comparator, which will actually compare this control voltage with this, and the same kind of action will be achieved that we have behaviorally indicated a few minutes back. This part is solved. Comparator design, that's an analog problem that you will learn more in your analog course. So from power management circuit wise, this is the final circuit that we have for PWM. There are several challenges, of course. The design does not stop at getting a comparator. You need to have the proper type of comparator. I'll come into the intricate design challenges a bit later on, because then you'll find that in cutting edge what all things you have to do in order to enhance your performance. So basically it's a comparator. It's done. Now we'll be going into the controller. Before we go into the controller and control system design, We have just right now mentioned the basic effect of the controller, but there is more to it than meets the eye. You have seen that it is minus k into V out minus V ref, but it's not all that simple. Okay, that k is not k only, it may be various kinds that I will be showing, and how to design that error amplifier to suitably get your proper behavior. So it's not that straightforward. Let's see, this is an open loop converter. When we say open loop, yes, this is another term that you will find, open loop and closed loop in terms of control system. When we say open loop, it means there is no controller. It's open, nothing is controlling it. And when you say closed loop, we say that there's a controller which is actually taking the feedback and taking proper action. So when a converter, buck converter is operating in open loop, it will actually take some time to reach its steady state. Okay, so this capacitor needs to be charged up to that voltage, the inductor needs to be charged up to that current, and these will actually like this charge, discharge, and slowly it will reach a periodic operation. So this thing is called the dynamics. There is a certain dynamics involved in the behavior of the converter. Similarly, say we will talk of load transient. Right. Say this is the converter output voltage. This is V output, and let's say I output. This is the current demand. This is right now 0, or I mean, you know, it can never be 0. It will be your what we call leakage current or standby current or quiescent current, whatever you call. So it's say this much. Suddenly that huge current demand comes, the maximum possible, this big. Now what will happen at that time? We need to ensure that this continues at this level, but it won't. Instantly it will drop, right? And then it will kind of take some time to stabilize. This is unacceptable. What should our controller do? Our controller should ensure that this thing gets settled quickly, like this. A controller should ensure that something like this might go very quick, and then minimize this overshoots, undershoots, this variable time and all. You cannot eliminate it, but you have to minimize it so that you get a fast transient, so that your processor, say, does not malfunction for a long time. So for a small time, as quickly as possible, you will have to settle it. Okay, so these are the transient effects that are that go on inside a converter and which need to be properly addressed when we design the controller. Now let's see what are the objectives of the controller design. To minimize startup overshoot. Well, you see here, it's a very ideal kind of startup that we have shown here. It may be sometimes that this thing goes high, right? Like in any your second order system. It depends on the damping and other factors, right? So this is a second order system. So what will happen during startup? It might be that it will go in a huge overshoot. This thing has to be eliminated, and during startup the huge current will also be drawn. That also cannot be tolerated because your power MOSFET device might get burnt up if it draws up huge current during startup. So there is something called soft start. We call it soft start. You need not go into depth of how to design a soft start circuit, that I won't be discussing, but simply know, just get yourself acquainted with the term soft start. Soft start means it will actually take some control action, so this does not happen. It will do it something like this. How to do this? It will actually vary the duty cycle. Now when I say this much, this huge dynamics, it's assumed that, suppose say this is the V out, this is the desired V out, and this desired V out gives us D. This is the required D. If from the very start we keep on switching at D and nothing else, only D, then this kind of behavior occurs, right? So what will the controller do in case of a soft start circuit? It will manipulate this D. How to? You need to reduce this. So it will actually reduce the amount of D. Got the point? So in this way the controller will act, or it might, if there is an undershoot kind of thing, it might increase the D. In this way it will soften the effect of the starting. So this is soft start. Now stability. Well, here is something that needs to be discussed in a bit detail. This term phase margin is mentioned here. Stability, and for fast dynamics there has to be an optimization of phase margin. Now forget power electronics for some maybe say for 15 minutes and just look at control systems. This phase margin is a very important thing. Now what is phase margin? Say you all have the concept of negative feedback, I suppose, because this negative feedback is what actually stabilizes a control system. There is I won't say controller, I would say the entire stuff. Say C plus P, that is controller plus plant, and this comes here. Suppose there is a disturbance, right? So what will make it unstable? If it at all becomes unstable, disturbance and noise in between. The function of the loop is to ensure that this noise gets rolled out, it gets eliminated from this loop and it remains stable. So that's what has to be done. Suppose there's a small sinusoidal noise. See, I mentioned this point as 1 and this point as 2, right? Suppose this is 1, right? Now since this is a negative feedback, you all know that when does a system become unstable? When it runs into positive feedback. Okay, so we have to see that under some conditions, under what conditions this negative feedback might actually start to behave like a positive feedback. When will it be? If after passing through all this, if 2 becomes like this. Okay, so that means it gets, just drawing is not proper, but I think you get the point. If it gets a 180 degree phase shift, if from 1 to 2 there is a 180 degree phase shift, what will happen when this comes here in 2, and if the negative thing, the minus will invert this and it will actually become a positive feedback and system will become unstable. Hence, whatever phase, this entire compensator plus plant, this system will add some phase into that noise. So if you take the transfer function of this entire thing, there will be 2 parts, your magnitude and phase. When you consider the phase, this much phase will be added to 2. You must ensure that this phase does not add up to 180 degree. So suppose suppose this phase all right, yes, another thing, when you do this positive feedback, when I say this positive feedback, you must you should remember that I consider sinusoid of equal magnitude, right? If it's a smaller magnitude, it will actually not go on adding that much because it will reduce slowly. So when I consider equal magnitude, that means we are considering a certain frequency in which the magnitude will be equal and the phase will be 180 degrees. So I write recipe of disaster. Recipe of disaster is equal magnitude and 180 degree phase. So I must ensure that this situation does not arise, right? So when will this situation not arise? Equal magnitude means, say, gain is 1, right? So what is, now if I take the Bode plot, if this is the magnitude Bode plot, say asymptotic Bode plot I consider, you have to consider this point. We call it UGB, unity gain bandwidth. Okay, we consider this point. This is the frequency of importance, this is the frequency of interest in which you have to save your controller and you will have to save your system. Suppose now I consider the phase at this frequency, right? I'm just drawing it not to scale, just something I have drawn. Say this is the phase and this is the 180 degree line. 180 degree line, this is minus 180 degree rather. So I consider, when you consider the phase diagram, you will have to accordingly take care of the minus and plus. In some cases, some books they will do it upper, and in some cases they will do it lower. So I just considered this. Here at this frequency, it is say minus 120 degree. So is it stable? Oh, it has gone outside. This should not have actually. The margin is somehow all right. I'll write again here. All right. Just ignore this arrow. I have marked the camera margin by this. Okay. So this is the UGB, and suppose this is the phase. So what will happen? And say this is the 180-degree line. So we have this much. This is say 120 degree. What do we say? It has a phase margin of 60 degree. What does this mean? An additional phase of 60 degree might yet be introduced into the system, and it may still continue to be stable. That's it. So that means this system is stable by 60 degree. This much phase is introduced by the plant, and another 60 degree phase might be introduced by the noise, and yet the system may continue to be stable. That's the concept. So when I look at this, stability, high phase margin, obviously as high the phase margin, more stable your system is. Suppose if I say that this is 100 degree at this point, you have room for an 80 degree phase disturbance. So more and the higher the room for your phase disturbance, the more stable your system is. Now just I'll ask you, is it good to have a very stable system? When I say a system is stable, there may be a threshold. Okay, so this much I need, and there is something called over design. So when I do more and more stable a system gets, also its dynamics gets slower and slower. We need a fast system. So fast dynamics during load transients, because then as I have already shown you, when the transient occurs, the overshoot, undershoot, that stabilization period should be minimized. So when it's fast dynamics, you need phase margin not too high. As low the phase margin, faster the dynamics. So you will need to have an optimization. As a thumb rule, which has been derived through years of experience by designers, we consider that an optimum phase margin of 45 to 60 degree must be maintained. Don't go below 45 degree, and don't go above 60 degree. If you go above 60 degree, your system will be super stable and super slow. And if you go below 45 degree, it will be very fast and yet very prone to instability. So this is the thing you should maintain, phase margin. Now when I say you should maintain, that means there must be some way of actually setting the phase margin, actually designing your controller so that you get a particular value of phase margin. Let's look at how to design a controller. I will just do it a very general kind of example. I won't take any particular system and pole placements and all. Suppose this is the system that I will consider. Some basic thumb rules I will discuss. Okay, so this is minus 40 dB per decade, say, and at this point, what will happen? I'll find that phase margin is so and so, say 30 degree. I need to increase the phase margin, right? So how to increase the phase margin? One way of thinking is that, suppose if I reduce the slope to, I'll just tell of one action that you may take. There may be several actions, and tomorrow today only, as you are aware, today you have 2 lab sessions. So in the second lab session, it won't be a full lab session definitely. So I will just show you a small demo using the control system toolbox in MATLAB, how to actually place the poles and zeros. You may have heard of these terms: pole placement, lag lead controller, and sorry. So I am jumping because these will come in the control systems course. So just I will show you an example of how to place the poles and zeros. Suppose I design a controller having a pole here, and which will, suppose a pole here, and which will have a minus 20 dB per decade slope, minus 20 dB slope. What will happen? This thing will have a much smoother variation. When it's 40 dB, it's a sharp minus 180 to plus 180 degree in a pole, double pole, and when it's single pole, it will be much lower variation. Obviously, your phase margin will increase to some extent. Similarly, another action that you may take, you may wish to increase this gain, increase or decrease as may be the case. That will vary your phase margin. These are several handles that you have on your phase margin. How to actually do this, I will show you later, because you haven't yet have this expertise of calculating the poles, zeros and placements and all. So you may increase this gain, that's one handle. You may increase additional zeros and other stuff, because whenever you introduce this pole, you will find that the controller circuits topologies that we use, that will have associated zeros, which will also come into the picture when you introduce a pole. You cannot introduce an isolated pole or an isolated zero in your system. So when you do this, something else will get disturbed here. Say just say for example, something will get disturbed in the lower frequency, higher frequency regions. Then in order to correct that, you will have to introduce something else, another pole or zero, like that. You will have to introduce poles and zeros at suitable positions, and ultimately check whether you have the appropriate phase margin and appropriate UGB. Why UGB? UGB is under your control. You may have any UGB. So unity gain bandwidth. Sorry, I mentioned here. This thing I call UGB. Right, at the frequency at which your gain of your transfer function becomes 1, or it crosses the 0 dB line. So that is the UGB. So higher the UGB you have, faster your system will be. Okay, lower the UGB you will have, slower your system. In this way you will have to play with several figures, several factors. Don't get confused or afraid by these. This is actually very easy, and we'll show you later on. So this is the basic thing. So let's see what a controller may be. Thus, this error amplifier, which I have already shown in that behavioral diagram, it will have the transfer function AS equal to minus Z2 by Z1. When I told you that it's not so simple as minus K into V out minus V ref, there is more to it than meets the eye. It's this that I mentioned, that this K can be any of these. It may not be a simple gain. If it's proportional control, there will be a simple gain. If it's PID, there will be Ki by S, there will be an integral term, there may be a differential term, and yet there may be something others called type 1, type 2 and type 3 compensators. Just keep in mind these names. You need not worry about the topologies. Just know that each of these are this kind of op-amp based topologies in which several configurations of Z1 and Z2 are used. There may be one capacitor here, there may be one resistor here, something thrown up here. And you all have sufficient expertise in circuit analysis that if I give you this topology, you will get the transfer functions. So I am not showing you any topologies. You just listen that there are something called type 1, type 2, type 3, and if time permits, I will show you the structure, and if not, you may do a Google search, you will get the topology of type 3, or in any your power electronics book, you will have your Maximovich book, there also you will find what are these. So the basic idea is, the error amplifier will have suitably designed Z2 and Z1 so that we can put suitable poles and zeros at certain places. Suppose your AS, there is a general AS, this is the most common that we follow. It will have 1 minus Z by P, S by Z1. Sorry, this looks very bad. A 1 minus S by Z1, there will be 2 zeros. This is the most common controller that we use. Leave aside the topology, you can solve it and get this structure. And then S by, there will be 3 poles. This is the type 3 compensator, or maybe type 2 also. I am a bit confused, so don't get hooked onto that type 1, type 2, type 3 terminology. Check it for yourself. So there will be 3 poles and 2 zeros. This is the most common compensator that we use in most on-chip buck converter design. And there you will have to place these poles and zeros accordingly to get your proper phase margin. And then once you have these poles and zeros, you have your equations in terms of R1, R2, R3. Like say there will be P1 is a function of say R1. There will be 3 R's in the circuit. R3 and maybe some C, something like this. Similarly, all these will have its standard expressions, and you put in the values of Z1, Z2, P1, P2, P3 arrived from your control system analysis and get the proper R2, R1, and then you have your error amplifier ready. So that's the way we get our controller. Now, looks a bit frightening, but this is the real thing that happens. What we have discussed is a more rudimentary structure. There are several things. I won't discuss all of these. I will discuss some parts. Compensator, we have already seen. VI reference generation. I have always assumed that there is some reference voltage called reference voltage of 1.2 volts. But getting a reference voltage is not that straightforward. You might have gone through your band gap reference course in your analog, or I'm not sure if you have, but just keep in mind that there is something called reference generator circuit, which is a very simple circuit. If you have already gone through it, then okay, you will understand. If not, they will discuss it in the coming analog lectures. Reference generator, so there will be something for generating the reference. Why we call it reference? Because it has to be maintained constant. It won't vary with temperature, it won't vary with your chip input voltage, it won't vary with anything. So that's why it's reference. Then there is PWM comparator. Something called logic controller. Why is this required? This is required because you will have to, other than controlling your system dynamics, you will have to take several actions like switching off your parts of your circuit when you are in standby. A mobile phone, most of the time it's in standby, it will draw large current only when you get a call. So on an average, its power consumption is very low. So even if you can switch off the most parts of the circuit when it's in standby, then you may seem that only small amount of power is saved, but in effect, in percentage of the actual consumption, that is a big saving. That's why this logic controller, what it does, it controls the soft start, as I say. It will take in various, it will do current protection, it will over current protection, it will, under voltage lockout, several other protective actions this one will take, and switch off certain parts of the circuit if necessary to conserve power. Several such, any kind of your decision may be taken, so hence this one has to be there. Gate drive. So long as I have mentioned that MOSFET is switched using a switching signal, but if you just get a switching signal, a square wave out of your, say, comparator your LM339 or whatever you have, you cannot put it into a MOSFET and your MOSFET won't run, because MOSFET gate requires large amount of current to charge it up. MOSFET gate has huge input capacitance, right? Hence this driver circuit. And something called dead time controller. I would like to discuss this dead time controller in a bit more detail. I'll leave aside the driver because you can't discuss all these. Driver is a pretty simple thing, or you may get to know in due course. You can study on your own, but dead time controller is important. Say this configuration, we call it the synchronous buck converter because this has two switches. There is something called asynchronous buck converter, in which the second switch is replaced by a diode. That one which will be taught to you first in your I think it has already been taught. Power electronics is over in, say, second year. Oh, it has not? It's in third year. Okay. So you will be taught your diode. This one will be. So that we call asynchronous. Ultimate effect is same. So what happens that there is a path for shoot through. What is shoot through? Just see. One goes off, the other one goes on. There is a small amount of time in between which there is a possibility that both of them are on. And when this is there, there is the possibility of huge current peak. And this peak current may burn the device. So that's what we don't want to happen. And also this peak current drawn from the supply, it will suddenly pull down your supply voltage and create various other unnecessary disturbances. So that's not allowed. How to protect this? Break before make. We first break the first one, wait for some time, and then make the first one. Then who operates in between? In between, both are off. How will your circuit operate? Just go back a bit. There's an inductor. What will happen if both of these are off? Inductor gets open, and in steady state, can you suddenly break off an inductor? Inductor will act as a current source. So something has to sustain the current. This current that flows here, it has to be sustained. This one goes on through the body diode. All these MOSFETs have a body diode, parasitic diode. I won't call it parasitic because this is a useful function, but well, it's not intended, but it comes. So what will happen? This will circulate through this. When both of these are off, this will circulate through this. And when this current has died down, ultimately, why will it take some time to die down? Because there is a capacitor here. This current will die down when this capacitor will charge up. Okay. When I break it open, this capacitor will be charged up by this current that was already there, and once this capacitor charges up to a certain V in, this current becomes 0. So this takes some time. Till that happens, this circulating current is supported by this body diode, and once that happens and sufficient time gap is provided for that, we switch it on. So there is no shoot through. So this is called the dead time controller, and this is the realization that they have done, that they generally do for your this dead time controller. There will be a NOR gate and there will be an AND gate, and these are the switching signals A and B. The switching signals generated from your controller, and these switching signals are a bit shifted. These shifted switching signals generated from your controller passed through these gates and then to the driver will actually generate this dead time. And then how do you shift this switching signal? You calculate these values, and this is the way you actually schematic of a dead time controller. When you get this switching signal, there's a dead time delay. This delay, this will delay the B by a certain extent, and this you get this VG1 and VG2 after acting getting this delayed A and B. So this is what the dead time controller is all about, and this is very important. I'll show an example. This is a experimental waveform from one of the converters that is designed in our lab. This is a high frequency converter. It's a high frequency converter operating at 20 megahertz, and it has good efficiency of the order of 80%, designed by Mr. Ashish Maiti. So this converter, this is one of the test waveforms from it. These are the gate. This has been implemented, this dead time. You will see this is the dead time delay, and this is the gate driving waveform, and this delay is thus implemented in this. This is the order of the dead time. You just follow the time gaps. This is 400 nanoseconds. So this will be something of the order of, I think, 15 to 20 megahertz kind of frequency, and around 25% duty cycle. So just estimate the time. I have shown this dead time here so that you can estimate the amount of dead time that is required in contrast to the amount of on time. So this much amount of dead time you have to provide in order to protect your circuit. This is a real design that we have shown. Well, that's all about your behavior of the converter and how to design the controller of the converter. Now, before we go into the layout of an actual power MOS, I would take you through the design steps of how to get the power circuit. We have been talking about the controller, but I haven't told you anything about how to get the L and C values of your power converter, right? So let's design the power circuit. That's several small steps are involved. First, we will note down the specifications that have to be adhered to. First is V out, okay. Then delta V out. These are all specifications. Delta V out means ripple. Say it is 20 millivolt peak to peak. Just say it may be anything. V out may be 1.2 volt. This is, I am stating the specification of the high frequency converter that I just mentioned. All right. Switching frequency. This is a specification. Of course, this is specified by the user or maybe your customer. They go to higher and higher switching frequencies so that you can reduce your passive size. Your LC values will be small, and you can integrate the entire thing on a small board. I'll be showing you a board photo, and you'll get to know how small it actually becomes. So F switch, let's say 20 megahertz. Then delta I, inductor current. Inductor current will actually charge and discharge between D and 1 minus D, as you have already seen. So this is the delta I. This is specified. This is very loosely, you have lot of space, 30%. That's huge, you may think, but this is generally, we are very relaxed in terms of deciding the specified inductor current ripple. Okay, say 30%. And we have the V in. Having all this, how to go ahead? First step. Step 1. D equal to V out by V in. That is the first step. We get D. Step 2. We need to decide the value of the inductor. So these three or four steps, we will get the value of the inductor and the capacitor. Step 2, what will you do? You solve this geometry. You will get D by F switch just remember that f switch is equal to 1 by Ts. When I say that this is Ts, this is d by Ts, this is delta I as specified, 30% of course IL, 30% of something, this is IL, this is specified. So L di dt, and delta V is V out minus V in. At this time it gets V out minus V in amount of difference in voltage we did in volt second balance portion. Delta V equal to L di dt. L into di dt is the slope. Say di dt I write. This is IL. This is di dt. From there we know V out, we know V in, di dt we know, get L. Done. This is step 2. Now we will go to step 3. Here I want to mention that I will be telling you, since this is a VLSI course, I will tell you in terms this capacitor, the way of getting this capacitor, an equation that I will be telling you, you will find that when you enter your power electronics course, you will get a different kind of equation. But don't get confused. I will tell you both the methods. But firstly, I will tell you what we should follow in the VLSI domain and why, and what you will get in your power electronics course, so that you don't get confused. Firstly, what we do, remember that each inductor has, the ideal inductor does not exist. There is something called ESR, and similarly ESR for the capacitor. Inductor ESR is not that important, okay, but you have to seriously consider the capacitance ESR. Why? There is a standard thumb rule, okay. C into R ESR equal to constant. This is a standard thumb rule. This value of the constant, this varies from manufacturer to manufacturer, right? So what you will do, suppose you have you take any, say you will put Philips capacitors or Murata capacitors or whatever, you go through the data sheet and you will find that C into R ESR is more or less a constant. So for a thumb rule you consider this constant. There is also something, I think I forget the value, which there is a more widely accepted value which does not match with many of the manufacturers, but which may be assumed. I think it's 6.3 mu or something of this kind, but I tell you I am a bit confused with this value. It actually happens, wide range of values come, because there are very low ESR capacitors available in the market, some high ESR capacitors, this K will vary. Now what you will do, once you have delta I, what you will do, delta V, this is the expression you will, delta VO, this is the expression that you will consider, delta I into R ESR. Thus actually the amount of output voltage ripple is getting decided by the ESR of the capacitor and not by the capacitor. This is where I would like to point out to you that this is where it will differ from what you will encounter in your power electronics course in the first time when you go into third year. There what you will be taught that your output voltage ripple is decided by the capacitance and not by the ESR, okay, by the capacitance. So C dVdt kind of expression will be taken, C dVdt equal to I kind of expression, and from there you will actually get the capacitor from your delta V specification. But here we are getting the ESR. I will tell you the difference, why so. Delta V naught equal to delta I into R ESR, from there you get the R ESR, okay. And once you have the R ESR, you feed into this expression, ESR equal to constant, and from there you get the C. This is the design steps that we follow, right. Now it may seem counterintuitive to you. Why? Why C dVdt equal to I, this expression, why not considered? This has not been brought into the picture at all. So are you ignoring the capacitance? So this is not, because you must remember that when we are doing VLSI, we are actually doing high frequency. It may be, we are talking of 20 megahertz, we are talking of 8 megahertz. This is a production, this is in production, this converter. I forgot the manufacturer, and so it's all in the order of megahertz. And when you are doing your discrete level, in your power electronics lab, basic lab, the converter that you will be experimenting with, that will be running at something of some kilohertz order, okay, 20 kilohertz, like that, maybe at most 100 kilohertz you will be doing. So when we go to higher frequencies, when you go to higher frequencies, your C behaves like a resistor, behaves like resistor. This C behaves like resistor or inductor. The main, when it's a C, in your higher frequency, the C effect reduces. Okay. Capacitance, the ESR effect, it becomes more and more dominating when you go towards higher frequencies, and in lower frequencies, the low frequency capacitors, the ESR is very less, the capacitance is higher, much higher. So the C DVDT kind of, the DVDT that comes from your C, that is much larger in comparison to the DVDT that comes from your ESR, whereas in the higher frequencies, the DVDT that comes from your ESR, that is much larger in comparison to the DVDT that comes from your capacitor. So this is the reason, keep in mind, when you go towards higher frequencies, evaluate the ESR and then get the capacitor from that, and whereas when you are in the lower frequencies, directly evaluate the capacitor. So that's the way we design the power state. Power state design is done. Now that is done, I'll show you the layout. As has been mentioned, really nothing is visible from this, but this is just to give you a feel of what a total power controller IC, power converter IC might look like. So this is the layout of the 20 megahertz DC-DC buck converter in 0.5 micron BiCMOS process that's available with us and fabricated from NATSEM. You will find this is the NMOS and this bigger one is the PMOS. Really, as Professor AP had mentioned already, so that it's typically the PMOS is 1.5 times the size of the NMOS. So this is the PMOS, and these are the several drivers and the controller and all other circuits. About this layout, this one does not have any pin. So in traditionally any circuit will have, if this is the circuit, you will have several pads. Any standard layout, when you will be taught layout in your analog course, you will find that a typical IC will be like this. These will be pads and these will be pads. Pads will be inside the IC. These will be the pins. If these are the pins, there will be bond wires connecting to the pads. So there will be pad, bond wires connecting, and this entire thing will be the package. Pins are outside the package. So this is the thing. But here you will find we have actually designed this on a, this has been designed on a, this is called micro SMD, a micro SMD package. What is this micro SMD all about? You will find these small balls. So if you circular spherical things, these will ensure good contact, ohmic contact will be good, and these will these do not have any bond wires because these are not pins, these are directly bonded, to your die. So this is directly below the die. Hence the parasitic inductances and capacitances due to these bond wires are eliminated. When we say parasitics, at the order of in the 20 megahertz region where this IC operates, these bond wires contribute around 2 nanohenry, and these pads will contribute around say few picofarads of capacitance, which these might seem to be very less, these are significant, and these will cause a lot of disturbance. So in better, these are also called BGAs, ball grid arrays, which you might have heard of in your processors and all. They are all designed on BGA kind of structure. So this is the micro SMD layout. Packaging, several kinds of packagings, you can estimate the size of these. These are several of these micro SMD things that are shown, and this is what I had mentioned. The silicon would be in between and bond wires would be connecting to the pins, and hence as you can see, lot of parasitics, bond wires, pins, resistance, inductance, capacitance, everything. So high performance ICs cannot be packaged into these. This packaging is a bit more higher performing than this one because of the lengths of these are all reduced. This will be soldered on top on the board, and this is the highest performance. So this is the order. Two advantages of micro SMD over DIP. One thing that I can find out from here is the inductor, your parasitic inductance. Another one, can you tell? I would like the answer from you. Anybody? It's there in the picture only by looking at the, huh? Ah, yeah, that's right. Package space is very much reduced. Even with this TSSOP package, it might seem big, but when you actually take an SSOP 24 pin IC, say, and a similar IC 24 pin in a DIP package, you will find this to this is itself around 1/5 size, and when you consider this is even smaller. So you know, huge packing density and very small, really small boards you can have. Well, this is the micrograph of the die that has been fabricated, that 20 megahertz switcher. So a micrograph means this is taken from a scanning electron microscope. This your die, silicon die has been photographed. So these structures have more or less come out here. These are all about, and these are the your SMD pins. Well, this is the design of the test board. Design using the Eagle software. You can use ORCAD, and also just to give you a feel of how to go about. The typical design flow would be, first when you submit your IC, when you are through with your design layout and everything, submit your IC. Before it gets fabricated, in between parallelly you will have to design your board. Designing the board is very important because board will have lots of, you know, parasitics. You will have to provide for suitable test pins on the board so that you can see all other signals without actually touching the IC pins, because if it's a micro SMD thing, your IC pins itself won't be available. They would be somewhere bottom hidden from view. And if your normal thing, you can put your oscilloscope pin somewhere in a very tardy manner on the pin, but you know, if it's a micro SMD thing, you will have to plan properly. And this is what it actually looked like after getting fabricated. Just compare with the dimension here. This is a standard capacitor. This capacitor itself is so huge, and this small thing is the IC. So the test components themselves are much larger than the IC. So if this, since this is a test board, several jumpers are there, several points for connecting your probes are provided. So if this goes into a production and if this goes into an actual system, you can imagine the space it occupies, because these test pins won't be there in that case. This is the photograph of the test board. Well, we have come to the end of the presentation almost. Just to give you a feel, this is the test result of that IC, and this is the kind of waveform that we expect. This will be the inductor, triangular inductor waveform, and this is the gate drive and all, quite clean. So we expect that this kind of disturbances, you know, these are these ringings. These ringings have to be minimized. You will have to design your gate drives in such a way that these will be kept to a minimum. Well, that's all from me. Any questions? Have I managed to confuse you thoroughly? If so, then you have the opportunity of confusing me. I will be meeting you again, I think today evening, with the control system toolbox demo MATLAB. You are open to you know, discuss anything that you might not have understood from this. Okay. The first session of the lab is as it happens, 2 to 5. The second session, I have not been told as it. Okay, just wait for a few minutes. I'll get the information. Could you just get me